In this video we're going to be looking at finding turning points for functions and using the second derivative. To begin, we'll use this polynomial. It's a cubic, it has a maximum and a minimum point. Of course, we begin by differentiating this function once, finding out where is equal to 0, and that will be our maximum and minimum points. The first derivative set it equal to 0, and this will give us x is equal to negative 2.431. That will be our maximum point, and our minimum will be 1.097. Now, how do we know this first point is a maximum, not a minimum, without looking at the function? Well, we know that this point here, if we plug it into the function, negative 2.431, plugged into the original function, then this will give us a value approximately equal to 16.9. So this is what we believe our maximum point will be. How can we test this? Well, one way of testing it is to take a point to the left and another point just to the right of what we think our maximum point is. And we'll plug those numbers in where we originally plugged in negative 2.431. If both these points give us a value less than 16.9 on both sides, then when x is equal to negative 2.431, this must be a maximum, as the other points are lower than it. And the same thing applies to 1.097. If we take 2 points either side and they're both bigger, then we must have a minimum. But there's another method. If we remember that the first derivative is the change in the function, then the second derivative must be the change in the change function. We call this one the gradient. So the second derivative, it must be the change in the gradient. If we look at this first point, it's steep and positive. We'll take another point further along, still steep but less steep, still positive. Next point, less steep again, then less steep, and then 0. Positive all the way, but getting smaller and then ending up at 0. If we keep going, it's not very steep, but it's now negative. Here it is more negative, then more negative still. If we give these approximate numbers, then that could be 7, 5, 3, all the while decreasing, 1, then it's 0 in the middle, then negative 1, negative 3, and negative 5. What do all these points have in common? Well, as we go along, the derivative, or the gradient, is decreasing all the way along. So the change in the gradient, for this whole section here, the change in the gradient is negative because the gradient is decreasing. So here we can see the change in the gradient has to be less than 0 because it's a negative change. Which means at this point here, where the first derivative is 0, has to be a maximum or minimum. We know that it's the top of a hill, so it has to be a maximum, which occurs when the second derivative is less than 0. This other point we have when the first derivative is equal to 0, that's a turning point. But if we look at the gradient, we can see that these gradient points, they're all increasing. So that's to say that the second derivative is now positive or bigger than 0. This means we must have a minimum. Another word for this is concave up or concave down for our maximum, and concave up for our minimum. There's one more point, and it's this point just here. So you can see this point is where the concave down bit finishes, but before the concave up bit begins, so it's neither concave up or down. That means that our second derivative isn't going to be positive, it's not going to be negative, but is in fact going to be equal to 0. We call this a point of inflection. So we can find a point of inflection by taking the original function. We'll differentiate it once. We'll differentiate it twice. And we'll find when this point is equal to 0. That's when we have a point of inflection. We can solve this for x. And we know our point of inflection is when x is equal to negative 2/3. So we'll take this, we'll plug it into the original function, and that will give us the y value. So this is the coordinates of our point of inflection.